Hi everyone. I hope everyone can hear me. Welcome back to the analytical chemistry series. My name is Dr. Matthew Waite, and this is the 11th lecture, which is on electrochemistry. Now, electrochemistry can be quite confusing, so we're going to go right back to basics. We're going to talk about energy, electricity, and we're going to touch on some mathematical concepts to help understand these relationships. As a sort of overview for what we're going to talk about today, electrochemistry is the relationship between electrical energy and chemical reactions, specifically redox reactions where there is a transfer of electrons. Electricity can be described such as potential difference of voltage in volts, current in amps, and these features can be used to describe reactions. And this means that electrochemistry can be used to quantify analytes. And really, you'll see that electrochemistry is a powerful tool in analytical chemistry. It's got high sensitivity, specificity, and cost efficacy. So first, let's remind ourselves about electricity. In a circuit with a cell, where there are more electrons on one side, which gives it a negative charge or negatively charged terminal, compared to another with less electrons, a positively charged terminal, this cell has a voltage. This represents the pull or driving force that attracts the electrons on the negative terminal to the positive terminal. And when the cell is attached to a circuit, the electrons can flow. And they will flow from this area of negative charge through to the area of positive charge along the circuit wire. You can see the flow of electrons with the arrows. Now, electrons carry charge, and they carry about 1.6 times 10 to the minus 19 coulombs per electron. And when an atom loses an electron, we say they gain a 1 plus charge, but in fact, they're gaining a 1.6 times 10 to the minus 19 coulomb charge per electron lost. Now, when electricity flows, it's not just one electron moving from one end of the circuit to another, more that as an electron leaves the negative terminal, one arrives at the positive terminal as shown, like that. Now, the voltage is the pull of the positive terminal from the negative terminal, and I've described that here like the size of a hill with boulders rolling down the hill. The amount that electrons can actually move around the circuit is determined by how easily they can move through the wires or conductors to get back to the positive terminal. This is the resistance, and I've described this here like the slope of the hill. So although there's the same voltage on both of these, you can see that these electrons will move around the circuit faster than these electrons because of the resistance to their movement. And the number of electrons that pass a particular point in the circuit per a second or per unit of time is known as the current. Now, despite a similar voltage, the movement of electrons naturally will be slower here than it would be here. Now, this brings us on to some equations. First, the voltage is related to the current and the resistance by V equals IR. This is obvious if you think of the resistance as blocking the flow of electrons that is driven by the voltage. Now, resistance can actually be necessary in circuits. It's what creates heat as electrons bump into other atoms. For example, how filament bulbs work is the resistance in the filament creates heat, and when the filament gets to a particular temperature, it begins to emit light. Now, electrical work or energy in joules is the current multiplied by the voltage multiplied by the time. This is how much energy can be transferred to a circuit component such as a bulb. Now, also note that the charge transferred is equal to the number of electrons that have passed a particular point in the circuit multiplied by their charge on a single electron. And this is the same as the current, the number of electrons that flow, multiplied by the time. So how many electrons are actually moving past a particular point in the circuit over a particular time. Now, let's move on to redox reactions, which are chemical reactions where there is an exchange of electrons. I've included an oil rig here to the left. As perhaps you will remember, oil rig is oxidation is loss of electrons and reduction is gain of electrons. In a redox reaction, one species becomes oxidized and another will become reduced, and that's where the electrons are transferred. Now, let's have a quick look at this reaction. So we're going to add copper sulfate to solid copper sulfate to an aqueous to water, and that produces a blue solution. Aqueous copper sulfate is blue. And next we're going to add zinc, solid zinc, into the beaker, and you'll have to believe me that they mixed it, and then it turned like this. So the water is now see-through. It's lost its blue color, and then there's a black solid on the bottom. Now the color is gone, and a chemical reaction must have taken place. Now what's happened here is that solid zinc has given up electrons to enter the solution as zinc 2+ ions, and copper has accepted these electrons to leave the solution and form solid copper. You can see that here. So zinc plus copper sulfate aqueous goes to zinc sulfate aqueous plus copper solid. Now the sulfate ions are actually unchanged in this. They remain in solution as sulfate ions, and so they're known as spectator ions. So we can split the two half reactions, what's happened to the zinc and what's happened to the copper, separately. So you can see that the zinc has become zinc 2+ and lost 2 electrons, and the copper has accepted these 2 electrons and become solid. Now, the question is, can you connect the copper to sulfate and the zinc by a conducting wire and allow the electrons to flow through that wire to allow the reaction to happen separated in space? And the answer is yes, and that's how electrochemistry works. Now, we're going to first of all talk about galvanic cells, and these are cells where the redox reactions are spontaneous. So a cell would produce electricity on its own. This definition will become a little bit clearer later. And by spontaneous, this means that the reaction would proceed if the reactants were not separated in space, much like the zinc copper sulfate reaction we just saw. Now, this is the Daniell cell. It uses the zinc and copper reaction, copper sulfate reaction we've just seen, set up in an electrochemistry format to harness electrical energy from the reaction. So you'll see that we've got a copper electrode, which is simply a sheet of copper placed in a solution of copper 2 sulfate. And on this side is a zinc electrode, a sheet of zinc bathed in a solution of zinc sulfate. The electrodes are then connected by a conductor that would allow electrons to flow between them. And the two solutions are also connected by a salt bridge. This is typically some filter paper soaked in saturated potassium chloride, but it can be other compounds too. And this allows completion of the circuit. If a negatively charged molecule, the electron, moves from here over to this side, then a negatively charged particle will need to move from the salt bridge into this solution to maintain charge balance. If there's no salt bridge, then placing this like this would create a charge buildup here and here, and nothing would actually happen. No current, so no electrons would actually flow around the circuit. Now, this is a slightly more simplified diagram. In the redox reaction, we know that solid zinc, reacts to become aqueous, and copper reacts out of the solution to become a solid. We've separated the reaction, but the exact same thing happens. So solid zinc, the electrode, is oxidized and loses electrons, and aqueous zinc is released into the solution here. These electrons that are released produce flow to the copper electrode on this side, where copper ions in solution accepts the electrons to become solid copper. And this attracts the electrons from the slightly negatively charged zinc electrode because of the loss of positively charged zinc ions in the solution. Now, to counteract the increased positive charge in the zinc solution, because of the Zn2 plus coming out into the solution, 2 molecules of chloride will dissolve in from the salt bridge. On this side, 2 molecules of potassium will dissolve in to counteract each copper ion that has become copper solid. Now, even though the K plus is moving this way into the solution, this is essentially a flow of electrons this way because there'll be more Cl minus left behind. And you can see the flow of electrons around the whole circuit here. Now, with this circuit, if it was just left like this, the reaction would proceed to equilibrium, separated in space. It could be used to power a bulb if we put a bulb here, but when the reaction really reaches equilibrium, the cell voltage will drop to 0. Because there is no further reaction happening, there will be no net current, so no net electrons flowing this way. So a bulb would light up and then would go out as the reaction moved to equilibrium. And I just wanted to prove to you that a very simple setup, a zinc sheet and a copper sheet in a zinc sulfate solution and a copper sulfate solution with a salt bridge, which is a filter paper, attached to the voltmeter, does actually produce a voltage. Very simple. Now, if you were to use a very high resistance wire here, or a very high resistance voltmeter, then thinking about V equals IR, the voltage that would be produced between these two these two cells, with a very high resistance, the current would be very, very small. That means that you can measure the potential, which is the voltage between the two cells. It's a measure of the voltage, the potential of the reaction, and it's related to the concentration of the ions, the reactants, and the products. Now, to measure this, so the voltage doesn't change, the amount of current must be tiny. A very, very small amount of current must be allowed to flow, so the circuit must still be complete. It's often confused that there is no current at all, but there must be a very tiny amount of current, and so it is important that the circuit is still complete. Now, this technique, where you have a very, very low current because of a very high resistance, so that you can measure a stable voltage, is known as potentiometry. It's measuring the potential of a reaction rather than measuring the reaction itself. Naturally, if the resistance wasn't very high, as the reaction progressed to equilibrium, the voltage would drop and soon go to 0. And this is the principle of ion selective electrodes. Now, I'm just going to remind you of Gibbs free energy. It relates temperature, enthalpy, and entropy to whether a reaction will happen spontaneously, where delta G is less than 0. At equilibrium, where delta G is equal to 0, and delta G is greater than 0 if it requires external energy to proceed. You might remember that delta G is equal to delta H minus T delta S. Delta, or H being enthalpy, T is temperature, and S is entropy. And remember that delta H being less than 0 means the reaction is exothermic, releasing heat, so favoring spontaneity. And delta S of greater than 0 means more disorder, favoring spontaneity. If you have a reaction, A plus B goes to C plus D, then the reaction quotient at any particular time is given by the concentration of the products divided by the concentration of the reactant. Now, it can describe any time before the reaction has got to equilibrium, or maybe when the reaction is actually at equilibrium. You can see that if the reaction is at equilibrium, the reaction quotient can sometimes be called K, the equilibrium constant that you might be more familiar with. But what that means is that if you increased the concentration of D, let's say, by adding more of the product D into the solution, then this would push the reaction to the left. Now, when you added more of the D, the reaction quotient would go up as the concentration of D rises. But as the equation re-equilibrates and moves towards the left and produces different concentrations of A, B, C, and D, this Q would go back to K. So it would move back to the equilibrium constant. And obviously, the equilibrium constant is only at a particular temperature. Now, to describe what happens with chemical reactions in terms of Gibbs free energy, the concept of standard conditions was defined. This is for ease, not because there's something special about this value, and it's described as delta G 0. Now, to measure this, each of the concentrations of the products and the reactants would be 1 molar. The partial pressure of gases, which is less relevant here, would be 1 atmosphere, and the temperature has to be at 298 K, which is about 25 degrees Celsius. Now, this situation is very much less likely to occur in reality. Naturally, it would give a reaction quotient of 1 if the concentration of both the products and reactant is 1. But it's basically the benchmark of defining reactions. But the Gibbs free energy under standard conditions will describe what a particular reaction will do. So if you place the products and reactants together at 1 molar, it may be that the reaction will continue to progress to the right, so more products, or to the left, so less products. And when equilibrium is reached, Q equals K, then Gibbs free energy is 0, as there is no ongoing reaction in one particular direction. No overall change, though obviously there may be some flux on each side. And remember that Q is not the equilibrium constant. It defines the ratio of reactants and products at a particular time. It can be before equilibrium is achieved, or it can be at equilibrium, where Q will become K. Now, I don't want to go too far into thermodynamics, but this is the second law of thermodynamics here. Delta G equals delta G0 plus RT ln Q. Now, this is an equation that can predict what will happen with reactions that are not at equilibrium based on the current concentrations of reactants and products. The delta G0 is under standard conditions and then is altered by the non-standard conditions, where Q is obviously the ratio of products to reactants, R is the universal gas constant, and T is the temperature in Kelvin. The delta G for a particular reaction changes logarithmically related to the reaction quotient from the delta G0. And you can see that when at equilibrium, where Q is K, delta G we know at equilibrium is 0. So delta G0 is oppositely equal to this second term, RT ln Q. The delta G0 is really a measure of how far the reaction is from equilibrium at standard concentrations and temperature. Now, going back to our Daniell cell, the separate reduction and oxidation reactions will drive electrons from the anode to the cathode. The energy or work produced by this process will be equal to VIT, which we defined earlier as being the energy that can be transferred by electrons. If you were to place a bulb, the overall energy until the reaction moves to equilibrium will be defined by the voltage measured times the current flown times the time. Now, this energy is equivalent to the Gibbs free energy for the reaction at that particular set of concentrations of the anode and cathode. This can be expressed a number of different ways. So the Gibbs free energy will be equal to the voltage times the current times the time. And we can express this as minus NFE. So N is the number of moles of electrons exchanged in the reaction. And F is the Faraday constant, which is the amount of charge on 1 mole of electrons. Therefore, minus NF is equivalent to the current times the time, like the NE I described earlier. And then the E is the potential, or the voltage measured on the cell is the same as the voltage term here. So delta G can be equal to minus NFE, and we can relate that back to our earlier equations about energy through circuits. Now, if we go back to our original equation here, the reaction quotient for this reaction is the Zn2 plus in the products divided by the copper 2 plus in the reactant. The solids do not hold concentration in solution, so move to 1 molar, and the sulfate is unchanged, we said, in solution. So although you can include the sulfate here and here, obviously those terms cancel because they are equivalent. Now, the relative concentrations of both copper sulfate and zinc sulfate define the potential of the reaction to progress. And we've said that delta G equals delta G0 plus RT ln Q. We've described that delta G is equivalent to minus NFE. That's equal to minus NFE 0, so the voltage at a particular, at the under standard conditions. And then our term RT ln Q, which says how far our current concentrations are from these standard conditions that will allow us to calculate our delta G. Now, if we divide all the terms here by minus NF, we get E equals E0 minus RT over NF ln Q. And this is the Nernst equation. Sometimes it's also written with a 2.303 here, which converts the natural logarithm to log base 10. So the E, measured as a voltage in volts, can be predicted from the relative concentrations of each ion in solution. So if you know the potential under standard conditions, and you know the concentration, let's say, of one of your solutions, then you can calculate the concentration of another solution. I hope that makes some sense. Now, as we said, potentiometry uses a high resistance voltmeter to reduce the current to near zero, so that the voltage is measured and does not change, and therefore you can calculate the unknown concentration of one of the ions in solution. Let's say we knew the concentration of copper sulfate, but we wanted to know what the concentration of zinc sulfate is here on the left. We could then relate this to the voltage, if there's a high resistance voltmeter, by the Nernst equation. Now, it's also important to think about electron flow when considering the salt bridge. I've already mentioned that a net potassium efflux into the copper solution allows a relative electron flow carried by the chloride ions this way, and it balances the positively charged copper leaving solution, and the chloride entering here balances the positively charged zinc entering the solution. Now, aside from the net movement of potassium here and chloride here, an important part of error in the measurement of voltage in this sort of electrochemical cell is something called junction potentials. Now, these occur when two solutions with different ions or ions of different concentrations come into contact. And this happens even before the circuit is complete. These junction potentials build up before the circuit is complete, and they can affect the measurement of the voltage throughout the entire circuit. So I'm going to show you that here. This is the salt bridge in green, and this blue is the copper sulfate solution or the zinc sulfate solution that the salt bridge is attached into. And what you can see here is that the chloride ions have a greater mobility in aqueous solution than potassium ions, and they diffuse into the solution faster as both are at higher concentration level diffused in. This creates a charge differential. It's more negative right next to the salt bridge in solution, and slightly more positive on the side of the salt bridge next to the solution. You get a slight positive charge and a slight negative charge. Now, this charge differential gives a slight potential that can impact the measurement of your voltage, and it may also change over time. It's well known that junction potentials, it's difficult to predict how much voltage or how much error you will get because of junction potentials. And it's not necessarily something that stays constant between different samples. Now, potassium chloride is often chosen as a solution for a salt bridge because the mobilities of potassium and chloride in aqueous solutions are very similar, which minimizes this effect. And the overall voltage that you'll measure is equal to the electrodes and the voltage that you want to measure, plus this error term, which comes from junction potentials. And aside from selecting ions with similar mobilities, calibration can eliminate some of the effects of junction potentials as well, but not necessarily all of them. Now, moving on, it may have already occurred to you that we measure the sodium and potassium with ion selective electrodes, but neither is easily reacted with a metal electrode. Also, serum from our blood is not a simple solution of an ionic species, which makes things more difficult. In fact, most ion selective electrodes use a principle that seems similar to a junction potential, but is more clearly defined by the Nernst equation. They use a membrane, and you can see that here, that is selective, but not completely specific to a particular ion. Within the membrane, inside, is a solution of known concentration of the ion of interest, and an internal reference electrode which reacts with the solution. This may be a silver chloride electrode, very commonly, with aqueous chloride or aqueous potassium chloride outside at equilibrium in solution, a known volume of potassium chloride in this solution, and then connected to another similar but different solution on the other side with an external reference electrode as opposed to an internal reference electrode here. Now on this side, there'll be a porous frit, which acts a bit like a salt bridge to connect to the patient sample, be high resistance, so very little current actually flowing here, but actually allows completion of the circuit so you can have current flowing the whole way around the circuit. So the important thing with ion selective membranes is that the electrodes themselves, the two reference electrodes, are not actually in contact or inserted directly into the patient sample, but actually both have membranes that allow interaction with the patient sample. Now, let's ignore the idea just for a moment that these electrodes are inserted into a patient sample and pretend the two internal solutions are connected by a salt bridge with ideal ion mobilities that do not produce a junction potential. The use of silver chloride electrodes are common in potentiometry as they provide very stable and reproducible potentials. They are used for electrolyte testing in blood gas machines, pH testing as well. In this situation, the relative concentrations of the surrounding solution in comparison to the silver chloride electrodes on both sides define how the electrons move. The saturated side balances further towards forming solid silver electrodes compared to the less saturated, but concentrated side. Now, considering each half cell, we can see that the chloride produced from the reduction of silver chloride electrodes will define the potential of each half cell. This is the standard potential plus the Lin-Q factor, which in this case is only defined by aqueous chloride as silver remains solid. The overall cell potential will be the potential at the cathode, where reduction happens, minus the potential at the anode, where oxidation happens. And I'm sorry that I have actually written, I've just realized, anode and cathode the wrong way around here. As I said, at the anode, the oxidation reaction will predominate, where electrons will be given up, and the reduction reaction at the other side. This produces electrons moving around the circuit. Remember that if the resistance in the circuit is very high, very little current will flow, and you will measure a voltage potential. So using the cell potential as being the cathodic minus the anodic, you can sub in each of this is the cathode and this is the anode here, and subtract, and these two terms cancel each other out, and RT over F ln CL1 minus RT over F ln CL2 is equivalent to RT over F ln CL1 divided by CL2 by logarithmic laws. So that will be the overall cell or the overall potential difference that you will measure in volts here. This is really important as it means that we have a fixed potential difference between these two electrodes, provided the internal solution chloride concentrations are fixed and different. Obviously, if the chloride concentrations are the same in both internal solutions, ln of 1 is 0, and therefore the voltage will be 0. So let's go back to thinking about this setup where our patient sample interacts with these two reference internal electrodes through the porous frit and the ion selective membrane, a little bit like the patient sample is the salt bridge as well. The important part of this is exactly what the ion selective membrane is doing and how this affects the overall potential of the cell. Let's consider a potassium selective electrode. So the ion selective membrane in this case is a hydrophobic polymer membrane such as PVC, and it has the antibiotic valinomycin embedded. Valinomycin is an ionophore, which fits the hydrated potassium ion perfectly. Thus, potassium from the internal solution can travel across the membrane, but other ions cannot. Naturally, we call these ions selective rather than specific, as there can be some impact from other ions, such as magnesium in the valinomycin electrode. Now, the pink area here is our ion selective membrane. This is our internal solution where potassium chloride is often at quite high concentration, let's say 1 molar. And this is our test solution where the potassium, which comes from a patient sample, where potassium will be at much lower concentration or physiological concentration. As the membrane is potassium selective, it prevents other ions from traveling down their concentration gradient. Potassium, however, will move down its concentration gradient. And this leads to a buildup of charge across the membrane that prevents the movement of further potassium molecules. The balance of charge is defined by the concentration of potassium inside and outside of the membrane. Now note that there's not really much real movement of potassium because of the charge buildup and the high resistance, meaning that the current is negligible. The samples are not spoiled by the use of these membranes. If current was to flow freely, there would be movement of potassium across the membrane, or a net movement of potassium across the membrane as electrons moved at the electrodes. It would be needed to allow charge stabilization, and then the solutions may be spoiled. Now, the membrane potential is defined by the relative concentrations of potassium on either side, again defined by the Nernst equation. Again, if you know the internal solution potassium concentration, you can see that you could calculate the sample concentration knowing the potential of the membrane. So the overall potential is the E cathode minus the E anode, which gives you the electrode, the internal electrode potentials, and then adding the membrane potential. And we've said that the potential between the electrodes is defined by the chloride concentrations, and then whichever ion your membrane is selective for will determine the ion selective membrane potential. Now, for example, let's say that our internal solutions connected here by the theoretical salt bridge gives you a voltage of 0.0387 volts. The concentrated potassium chloride sits at 1 molar, and the saturated potassium chloride here sits at 4.5 molar. You can also put in RT over F at 25 degrees and put in the relative concentrations, the 4.5 molar and the 1 molar here, and you should get the same voltage. You can actually predict the voltage based on this equation. Now, if we were then to place the system into the patient sample, we can calculate the K plus concentration in the patient sample. So when placed in, let's say that the voltage changes from 0.0387 and reads minus 0.100 volts. We know that the E cell is equal to the E cathode minus the E anode, which we just calculated, 0.0387, plus the ion selective electrode, and you obtain, and we know that the E cell is minus 0.100. Rearranging to find your E of your ion selective membrane, you can then utilize this value to work out the sample potassium concentration. And you can try this at home at a later point with a calculator, but you should find that your potassium of your sample becomes 4.5 millimolar. Now, when you calculate this, you have to have the potassium in the sample, so the external potassium concentration from the internal potassium concentration. And you have to count, you have to decide before you put your system inside a patient sample, which one is the cathode and which one is the anode. You will actually notice that before, if we assumed this one here was the cathode and this one here was the anode, and we got an E cell that was positive, the fact that we've placed this into the patient sample and got a negative E cell means that the electrons have actually started to flow the opposite way around because of the potential difference that has built up here. But that doesn't matter. But it's just important that before you place it into a patient sample, you decide which one is the cathode and which one is the anode. This allows you to decide the side that is your potassium sample and your potassium internal. If you'd assume this was the cathode and this was the anode, you'd have to flip this over. Now, errors that you might see in ion selective electrodes can be due to non-selectivity of your ion selective membrane, or it could be because of junction potentials that can build up here, or even at the porous fit here on the right. Now, other types of membrane are available other than potassium, and potentiometry-based ISEs are used for pH, sodium, potassium, chloride, magnesium, and calcium. Obviously, magnesium and calcium tend to be spectrophotometric methods in the clinical lab, but pH, sodium, and potassium very much use this potentiometry. And just really quickly mention dilution in the laboratory. Samples for potentiometry, we tend to dilute, and the reason for this is that it reduces fouling of the electrodes from proteins and other large molecules. And this is required because of the really high throughput of analysis in clinical labs when compared to perhaps lower level throughput on ABG or VBG machines. And it leads to the problem of laboratory pseudohyponatremia, which you don't tend to see on VBG or ABG, which Dr. Abdul Malik discussed last week in her lecture. Now, that effect does also affect potassium, but a 10% negative bias of potassium means that often the potassium still remains within the normal range, and so there's much less of an impact. But you do get pseudohypokalemia with this as well. It's just worth mentioning that. So to just conclude about potentiometry, it uses galvanic cells, which means no energy needs to be added into the system. Measures potentials, and those potentials can be directly related to the concentration of test samples. The ion selective membranes alter the potential from two internal reference electrodes, and that allows calculation of an unknown concentration of an ion. we calibrate to correct for changes in voltage between the two reference electrodes, and ion selective membranes can be designed to respond to a particular ion, which sort of allows them to be used for more purposes. So we've discussed galvanic cells, but electrolytic cells are the second that I want to discuss. Now, electrolytic cells use an input of energy to drive non-spontaneous redox reactions and measure features of the resulting circuit to give information about the analytes involved in those reactions. Now, there are a wide variety of applications for this. For example, continuous glucose meters use these principles to measure glucose in the interstitial fluid. Now, analyzers, like continuous glucose monitors, can be known as biosensors if they utilize enzymes or receptors to establish selectivity to particular analytes. The main two galvanic techniques I will discuss are amperometry and voltammetry. Both estimate the concentration of a particular analyte, but they differ in whether the applied potential or voltage is fixed or variable. Amperometry uses a fixed constant voltage, but voltammetry uses a variable voltage. So the general setup is shown here. The major difference, as mentioned, is the application of an external potential to the circuit. This means that electrons are driven to one electrode, which obtains a negative charge, and another electrode that has a relative lack of electrons. The electrons have moved to here, will have a positive charge. So the negativity and positivity of the electrodes are defined by the voltage applied and which way they are connected to the voltage. So the working electrode is often defined as where the reaction of interest will happen, and the counter electrode is important in completing the circuit, allowing electrons to flow. If, as in this case, the relative lack of electrons or positively charged electrode due to this external power source is the working electrode, then you would be interested in the oxidation of a species at this electrode, and oxidation is conventionally called the anode. Now, this can be confusing because electrons move in the opposite direction of potentiometry. However, the definition of anode is where oxidation occurs, and the definition of cathode is where reduction occurs. Now, a positively charged electrode will promote oxidation reactions, where species give electrons into the electrode. Conversely, the working electrode can be the negatively charged cathode, where the cathode will drive reduction reactions, where electrons are given to species. This is because the more sort of negative charge encourages the acceptance of electrons from species, and the sort of more positive charge encourages the loss of electrons from the species. That kind of reduces the activation energy for the reaction. So the idea of these external potentials driving reactions is what underpins electrolytic cell electrochemistry. Now let's consider the use or the measurement of glucose as an example using a biosensor. So the electrodes are placed directly into the patient sample. The working electrode is surrounded by a selective membrane, which allows the passage of glucose into the electrode surrounding area. Once inside, glucose oxidase enzymes associated with this area will bind to the glucose and catalyze the reaction into glucolactone and hydrogen peroxide. Now, at the working electrode, the relative positive charge will promote the oxidation of hydrogen peroxide, and the electrons released from this reaction into oxygen and 2H plus ions the hydrogen peroxide will obviously release the two electrons into the electrode and produce the oxygen and the 2H plus ions. These electrons that are released will be driven by that external voltage to the negative electrode via the applied potential that is there, because there will be a constant potential between these two electrodes driven by that voltage. At the counter electrode, oxygen will be reduced to water to complete the circuit, And this may be part of the explanation of why pressure on body sensors reduce accuracy because of the reduction in blood flow and the reduction of oxygen, and probably also because of the reduction in glucose availability. Now, it may be obvious that the current from the released electrons will be directly proportional to the glucose concentration, assuming the glucose oxidase enzyme is in excess, so the H2O2 or hydrogen peroxide production is actually related linearly to the concentration of the glucose in the sample. As there's more glucose, there is more production of H2O2, which means there are more electrons available to travel around the circuit, which means that the current rises further with an increased glucose concentration. And this is amperometry, which links the current measured to an analyte concentration. Now, voltammetry we mentioned involved actually changing the voltage, and this is represented by the variable cell symbol. However, the setup is very much the same. There are many different techniques for voltammetry, but let us consider something known as polarography, and this can be used with chloride measurement. So consider the reduction of chloride ions at the cathode. They will form something like chloride gas or some other form at the electrode. As the chloride ions are reduced, the chloride ion concentration around the electrode drops, and other chloride ions will diffuse in down the concentration gradient. If you were to continue to increase the voltage, this means that the electrode would become more negative, the working electrode would become more negative. This would speed the reduction of chloride ions. And I'm sure you can see that there would come a point as this process is going on where the speed of reduction is so quick when they approach the working electrode that the speed of diffusion of the chloride ions to the electrode will be the limiting factor for the reduction process. This would be seen as a maximum current in electrons moving around the circuit. And you can see this here. As the applied potential increases, the current increases as the chloride is more easily reduced, giving up its electrons to travel around the circuit. The limiting current as the current reaches the maximum is not defined by the ability of the chloride ions to be reduced, but more by their speed of diffusion to the electrode surface. This limiting current is directly proportional to the chloride ion concentration in the sample. Now, in fact, chloride measurement via polarography really tends to be used in research rather than analytical chemistry, and chloride measurement in the lab tends to use the principle of coulometry. Now, coulometry can be either with a fixed or a variable potential voltage, so it can be a subset of either amperometry or voltammetry. Now, a fixed volume of patient sample is added, and the voltage is applied, reducing the chloride at the cathode until the current goes to zero. Now, when the current goes to zero, that will be when all of the chloride in the sample has been consumed. Now, the amount of chloride can be calculated by considering the charge passed, which is the number of electrons that have actually moved around the circuit. The charge is the current in amps multiplied by the time that that's taken. Now, this would represent the area under a time current curve. The current would not be constant throughout this whole process because it will be defined by how the relative availability of chloride, which will change throughout the process. But the charge would be the area under the time current curve. The charge can then be related to the number of electrons passed by number of electrons is equal to the charge divided by Faraday's constant. This will give you the number of moles of electrons that have traveled around the circuit. And that will be equivalent to the number of moles of chloride reduced. And if you divide that factor by the volume used in the patient sample, then you will give you the concentration of the chloride used in the sample. Now, there are a wide variety of applications for electrolytic cells, Aside from biosensors, which are really a rapidly developing field, because you can include multiple different chemical reactions and measure them via electrochemistry, which is already used in CGMs, glucose and lactate in the blood gas. The oxygen sensor in blood gas uses this approach. Chloride uses these approaches, and voltammetry can be used for trace metal detection as well, typically via different techniques that I haven't shown here. So, in conclusion, electrochemistry provides really powerful tools for analytical chemistry. Galvanic cells allow spontaneous redox reactions to generate electricity, which can be described with voltmeters to identify the concentration using the Nernst equation. Analytical galvanic cells tend to use potentiometry, which really utilizes a really low current flow. Electrolytic cells utilize external energy to drive non-spontaneous redox reactions. And these electrolytic cells have a variety of applications in analytical chemistry. And as always, please feel free to reach out via email if you have any questions or you need any further clarification. And please put any questions into the chat if you have anything. But thank you very much.